Now it starts to get interesting. Yeah? With 2-qubit gates, you can, of course, do much more than with single-qubit gates. The general structure is as follows. You have now 2 qubits coming in. Together, they are in some 2-qubit state psi. The 2-qubit gate performs a unitary transformation in the 2-qubit Hilbert space. So that's a 4-dimensional Hilbert space. And out come 2 qubits in the transformed state. The 2-qubit state that's coming in can be a product state. So each qubit individually is in a pure state, either a basis state or some superposition state, and but they are not correlated. Yeah. So we have a product state. There's a separate state for each pure state for each qubit. But the input could also be an entangled state, like the Bell states that we discussed last week. The same holds for the output state. Yeah, that can also be either a product state or an entangled state. That's all possible. The unitary operation that's taking place, as I said, happens in the 2-qubit Hilbert space. It's a 4-dimensional Hilbert space. So in the standard basis of this 2-qubit Hilbert space, this is represented by a 4x4 unitary matrix. The most important 2-qubit gate that you will find in a quantum computer is the so-called C-NOT gate. It stands for controlled NOT. And this graphic, so it's denoted by this symbol. So you have this, you have 2 qubits coming in and 2 qubits going out. Yeah. The first qubit, the upper qubit, is called the control qubit, and denoted by the state is denoted by C for control. Yeah. And the lower qubit, where the state is denoted by T, is called the target qubit. And as long as the 2 input qubits are in standard basis states, so C and T are 0 or 1, as long as that is the case, the control qubit, the state of the control qubit does not change. So the qubit going out, the upper qubit going out, is still in the same basis state C. But the lower qubit, the target qubit, its state may have changed, and it changes, it's flipped, if and only if the control qubit is in the basis state 1. So if the control qubit is in the basis state 0, then the control qubit itself remains unchanged, and the target qubit has the output state T plus C mod 2, so that's T plus 0, which is still T. So then the target qubit state doesn't change either. If, on the other hand, the control qubit is in the basis state 1, and then the target qubit, its state changes from the basis state T to T plus 1 mod 2. So 0 becomes 1, and 1 becomes 1 plus 1 mod 2 is 0. So basically, the basis state is flipped. That's a logical knot. That's why it's called a controlled knot. Depending on the basis state of the control qubit, the target qubit is flipped. So it's a logical knot, classically, or not. when you write the state of the 2 qubits in 2-qubit Hilbert space, then that's CT. So that the upper qubit is the first qubit in the cat, and the lower qubit, the target qubit, is the second qubit in the cat. We talked about control and target and the addition mod 2. The matrix representation of the unitary operator that's doing that transformation in the standard basis has this form that you see here on the slide. It's shown first as a 4x4 matrix, or in a more compact notation as a 2x2 matrix, where each entry is in itself a 2x2 matrix. Yeah? So you have the 2x2 unit matrix in the upper left corner and the Pauli X matrix in the lower right corner. Yeah, and then from this 4x4 matrix, you can see precisely what this gate does for each basis state in the 2-qubit Hilbert space. So whenever the control qubit is in basis state 0, then nothing changes. But if it is in basis state 1, then the basis state of the target qubit is flipped. The fact that this 4x4 matrix is unitary is also the proof, the evidence that there exists a unitary transformation which performs precisely the operation that that we want to have, that I showed you in this graphic. Now here comes a question for you, and maybe you want to think about this for a minute. I'll take a little break for a minute and you think about this for yourself. When you input into this C0 gate, not a combination of basis states, but the control qubit is in the plus state and the target qubit is in the basis state 0. What is the output? Let me write the 2-qubit state that's going into the C0 gate. I mean, the plus state, that's this superposition of 0 and 1 with a plus sign. So so we have this product state, plus 0, and if I write the plus state as a superposition, then this is equal to 1 over square root of 2, 0, 0, plus 1, 0. So this is the 2-qubit state going in. The C0 gate, that's a unitary transformation. Unitary transformations are linear operations. They're linear operators. So they act on these two cats separately. So the output is the linear combination of the C0 acting on 0, 0. Now, what does the C0 do? The control qubit is 0. And therefore, the target qubit is not flipped. And therefore, the C0 doesn't do anything on the state 0, 0. This remains 0, 0. The second state, 1, 0, there the control qubit is in basis state 1. This means the C0 gate flips the target. So the target state is flipped from 0 to 1. The control qubit remains unchanged, right? It remains 1, and the target qubit is flipped from basis state 0 to basis state 1. So the 2-qubit state coming out of the CNOT gate is this state here. And this is one of the Bell states that we encountered last week. Yeah, this is the Bell state 0, 0, which is an entangled state. Yeah? So here you have an example where a gate, a 2-qubit gate, can produce entanglement. You have a product state coming in and an entangled state going out. Okay, then let me show you after the CNOT, let me show you a few more 2-qubit gates. One is very similar to the CNOT. It's called a controlled Z gate. And it's similar because the CNOT, the NOT operation, yeah, this flip of the target basis state, that's a Pauli X. We saw previously that the Pauli X is the quantum analog of a classical negation. It flips the basis state. So you could actually regard the CNOT gate also as a controlled Pauli X gate. Yeah? And the controlled Z works in the same spirit. Yeah? Depending on the basis state of the control qubit, the gate performs a Pauli Z operation on the target. Yeah. So once again, in this graphic, C and T are 0 or 1. Yeah. So they are basis states. The control qubit basis state remains unchanged. The target qubit basis state becomes or acquires a prefactor -1, depending on both the control qubit and the target qubit basis state. If both of them are 1, then the target qubit state acquires a factor -1 and otherwise remains unchanged. It's only this prefactor. Yeah? So if the control qubit is 0, then you see the -1 to the power C times T is 1, so nothing changes in any case. If the control qubit is in basis state 1, so if C is equal to 1, then you apply to the target qubit a Pauli Z. Now the Pauli Z, remember what that does? It does nothing if the qubit state is the basis state 0. So if T is equal to 0, then still the Pauli Z doesn't do anything. And if the T is equal to 1, then you acquire a factor -1. Yeah? So if both C and T are equal to 1, then you get the factor -1. That's the controlled Z. It has a matrix representation in the standard basis of the 2-qubit Hilbert space, which looks very similar to the previous one. Again, if we take this compact notation where the entries are themselves 2x2 matrices, you see in the upper left, it's again the unit matrix. In the lower right, it's now the Pauli Z instead of the Pauli X. Yeah, and you can imagine if you have a controlled Pauli Y gate, what that would look like. Then you would have the Pauli Y matrix in the lower right-hand corner. Now there's an interesting identity. You can prove that for yourself at home. Maybe it's a very simple calculation that this matrix representing the controlled Z gate can be written as the product of these three matrices on the right-hand side, involving the matrix representations of the Hadamard gate, that's the H, and the in the middle you have the matrix representation of the C naught. Yeah. And this identity for matrices translates into an identity for 2-qubit gates. Yeah. On the left-hand side, that's the matrix representation of the controlled Pauli Z that we've been discussing. On the right-hand side, in the center, that's the matrix representation of the controlled knot that we saw before. And then the two matrices sort of between which the C naught is sandwiched with the H's in the matrix. These are the matrix representations of actually a single qubit gate acting on the lower qubit, on the target qubit only. Let's look at this 4x4 matrix, which I here write as a 2x2 matrix, where the entries are 2x2 matrices. So here you have the 2x2 matrix representing the Hadamard gate. And if you remember what basis states these are acting on. So this Hadamard here in the upper left corner, yeah, that maps the subspace spanned by 0, 0 and 0, 1 to the subspace spanned by the same basis vector 0, 0 and 0, 1. Yeah, so this Hadamard here basically has an effect inside the subspace. So the control qubit is in basis state 0, and it's not changed at all by this Hadamard. Now this Hadamard here has an effect only on the target qubit, on the second one. And likewise, if we look at the matrix down here in the lower right, yeah, its effect lives in the subspace spanned by 1, 0 and 1, 1 and maps to the same subspace, yeah, 1, 0 and 1, 1. So it is, again, a subspace where the control qubit doesn't change at all, and there's an effect only on the target qubit. Yeah? So the two entries here of the Hadamard matrix, in both cases, they have an effect only on the target qubit state, but they have no effect at all on the control qubit state. And their effect on the target qubit is also the same regardless of the state in which you have the control qubit. This is why here graphically the effect is simply a Hadamard transformation on the target qubit only, and the control qubit is not affected at all. Yeah. So here you have a first example of a relationship between 2-qubit and also single qubit gates. You can cleverly combine 2-qubit gates to construct interesting new operations. For example, when you have 3 C naughts in a row, where the one in the middle is sort of you flip the roles of control and target, yeah, then the net effect of these 3 C naughts is a swap of basis states. So if you come in the state AB, then you go out in the state BA. We can check that for a simple example. Let's say A is 0, B is 1. We go in with the basis states 0 and 1. After the first C0, the control doesn't change. It remains 0. And since the control was in the basis state 0, the target doesn't change either. So that's still in the basis state 1. Now, for the second C0, the roles of control and target are interchanged. So the lower qubit is now the control. The control doesn't change, that remains 1. But since the control is 1, the control qubit is in the basis state 1, it flips the target. So this state is flipped from 0 to 1. And then we go into the last C0. Now the upper qubit is the control again. The control doesn't change, so the output here will be 1. And since the control is in the basis state 1, it does flip the target from basis state 1 to basis state 0. So you see that the net effect of these 3 gates is that the state of the upper qubit became the state of the lower qubit, and the state of the lower qubit became the state of the upper qubit. The 2 states are swapped. And since this is a combination which occurs more often, it has its own symbol that you see on the right-hand side with the 2 crosses here, and that's called the swap gate.